This video introduces the concept of concavity, how to determine it using the second derivative, and how to use calculus to help you sketch a curve. If a function is increasing on an interval, its graph rises from left to right. But if it does so, a point on that graph, as it moves along the graph, moving from left to right, notice that the tangent line, at least in this case, see how the tangent line would be rotating clockwise? See how the curve that's created is like a spoon that is facing downwards? We call that concave down. If at the same time, on a different portion of the graph, as the point is moving along the graph left to right, still rising as you might notice that the tangent line, though, this time at different points, the tangent line would be rotating counterclockwise. See how the graph that's formed is like a spoon facing upwards. We call that concave up. Now, if the tangent line is rotating counterclockwise, that means the slope is becoming steeper, and therefore the derivative being the slope, that would then mean that the derivative must be increasing. So we'll say from now on that if a function is concave up, that's true if and only if, that if the derivative is increasing on that interval. For the same reason, we'll say that a function is concave down, or its graph is concave down, on a certain open interval if the derivative is decreasing on that interval. Now, if we ever get a point on the graph where before it has one type of concavity, and after it has a different type of concavity, and there's a tangent line to the graph at that point, then we'll say that this point is a point of inflection. What we need then is a test for concavity. But remember, though, that if I want to show that if a function is increasing, I can just take its derivative and see where it's positive or where it's negative. That would tell us when the function is increasing or decreasing. I want to know where the first derivative is increasing. So I'll take its derivative, second derivative, and I'll find out when it's positive. Wherever it's positive, on an open interval, the first derivative must be increasing, and therefore the function must be concave up on that interval. That gives us the second derivative test for concavity. Just let the function be some twice differentiable function on an interval. If the second derivative is positive on the interval, then the graph is concave up over that interval. If the second derivative is negative on the interval, then the graph of f is concave down over that interval. So suppose you wanted to know over what intervals is the function f of x equals x squared concave up. Well, to do so, all I need to know then is when is the second derivative positive and negative. So clearly, we need to know the second derivative. But in this case, the second derivative is always positive. That would mean that the graph is always concave up. In fact, here's the graph of the quadratic function x squared. See how it's always cupped upwards like a spoon facing upwards? But even though it's always cupped upwards, even though it's always concave up, the function is not always increasing and it's not always decreasing. So these concepts are not connected. Let's find out where this function's graph is concave up or concave down. To do so, we need the second derivative, and then we need to determine where it's positive and negative. Now, we've already answered that kind of question before. We'll just go and find where the second derivative is 0 and where it doesn't exist in the domain of the function. And then that would create subintervals over which each subinterval, the second derivative is either always positive or always negative. So I've already given you the second derivative, so instead let's just go ahead and find out when would that second derivative be 0, and let's just solve that for x. That would mean 36 x squared minus 1 all over x squared plus 3, that quantity cubed, would have to equal 0. Clearly that means then x squared minus 1 is 0, so x is 1 or negative 1. I also need to find everywhere the second derivative does not exist in the domain of my function. Well, but the second derivative is an expression that exists for every single x value, so you get nothing for that step. I'll draw a line that represents the domain of the original function. On that line, I'll put in 1 and, well, negative 1, and I'll put in negative 1. 1 and negative 1. I'll put the second derivative below the line, and I'll just evaluate intervals. In every interval, just pick a number, plug it into the second derivative. If you plug, say, 2 into the second derivative, you'll get a positive number. If you plug in 0 into the second derivative, you would get a negative number. And if you plug in, say, -2 into the second derivative, you would get a positive number. So I could say the graph of f is concave up, and that's on two intervals. It's from -infinity to -1, union from 1 to infinity. And I'll include the endpoints because of continuity. That's it. That's how you would do that problem. Here's another example of a function that I'd like to know where it's concave up, or its graph is concave up or concave down. To do that, I will solve that the second derivative is 0, and that'll be 4x. So that would then mean the only way this fraction could be 0 is if our numerator would be 0, and that gives you x is -4/3. That number, though, is not the domain of the function, because notice the domain is only those numbers bigger than -1. That's less than -1. It does not count. I'll find all x so that the derivative, our second derivative, does not exist. That can only happen if the denominator was 0, because otherwise it would be if this was 0, then you wind up dividing by 0, and that's not allowed. So that can only happen if the denominator here, that was equal to 0. And that's only possible if x is -1. But that number is at the edge of the domain, so we don't count it either, because we're going to get that number anyway. So the domain is only from -1 and up, and that's it. There's just one big long interval. So then just test this second derivative anywhere you want inside that interval. A good example then would be, say, 0. If you plug in 0, the second derivative would be positive. So this graph should be concave upwards always. So the graph of f is concave up, and that's on the interval from -1 to infinity. And that problem is done. Just like there's a first derivative test for local extrema, there's a second derivative test for local extrema. Let's just assume that the second derivative exists on some open interval containing c, and that the first derivative at c is 0. If the second derivative at c is positive, then f of c is a relative min, and if the second derivative at c is negative, that would then mean that f of c is a relative max. Otherwise, the test fails. It's considered inconclusive. The reason is that if you look at the functions f of x equals x⁴, look at f of x is equal to -x⁴, and look at f of x is equal to x³. For all these functions, the second derivative at 0 is actually 0, and yet for the first one, we have a relative min at 0, 0. At the second, we have a relative max at 0, 0, and the last one, we have no relative extrema at all. Also, this test is not as strong as, or cannot be applied to as many things as the first derivative test, because it insists that the first derivative at c is 0, while in the first derivative test, there's no such condition. All we need is that the first derivative is basically 0 or doesn't exist. More importantly, that it just changes sign and we have continuity. Also, the second derivative test is a little bit weaker because the result's weaker. In the first derivative test, we're guaranteed to know whether we have a relative max, relative min, or nothing at a single x value. Here, it could just fail. So then why would this test work at all? And what advantages are there? Well, the advantages are it's faster. If you look only at one number, this is much faster than the first derivative test. But why it would work? Well, just look at the second derivative. You know that it's positive. But you also know how to find the second derivative by definition. It's just the limit of a difference quotient, using the first derivative to do so. But we also know from the assumptions that f prime of c, that would be 0. So then I don't need to look at that portion, it just vanishes. So this limit is positive. Well, the only way the limit is positive is if for some interval around c, that for all of them, that quotient, that particular fraction, is actually always positive. Well, if x is more than c and near c, then this denominator would be positive. Since the fraction is positive, that means the numerator must be positive. And if x is less than c, then this x minus c would be negative. But since the fraction is positive, that would mean the numerator has to be negative. So the first derivative has to be less than 0 for x less than c and near c, and the first derivative must be bigger than 0 for x greater than c and near c. So by the first derivative test, we have to have a relative min at c. And that's the reason why if the second derivative at c is positive and the first derivative at c is 0, then we must have a relative min. And we can do the exact same proof for the other case. Let's find the local extrema of this function by the second derivative test. So I'll need to know the first derivative and the second. Once I find the first derivative, I factor it to make it easier for me to set it equal to 0 in order to find our critical numbers. Notice that the first derivative always exists, so there's no other places where we can get a critical number. The second derivative then, once I evaluate it for the first critical number and the second, notice at the second derivative at a half, you get a negative number, so you must have a relative max at a half, and at 3, the second derivative is 30, which is positive, and therefore we must have a relative min there. So we have a local minimum at x equals 3, and we have a local maximum at x equals a half. And that's how you would use that particular test. Now think of everything that we now know about the function because the first and second derivative. We know that if the first derivative exists, then the function's graph must be smooth and connected, must be continuous. The graph, of course, can rise or fall. If, though, we also know that the first derivative is positive on an interval, then the graph is rising from left to right, but it might be wavy as it changes concavity. If the second derivative is less than 0 the entire interval, then the graph will be falling, but again, the graph might be wavy because it can change concavity. If we know that the first derivative is positive and the second derivative is positive, then the graph would be increasing and concave up. If the first derivative is negative and the second derivative is positive, then the graph would be decreasing, falling, but also it would still be concave up. If the first derivative is positive but the second derivative is negative, then the graph is rising, but it's now concave down. And if the first and second derivatives are both negative on an interval, then the graph would be falling as you read from left to right, and it would be concave down. Also, we can find places where we have a point of inflection if we can find a place where the second derivative changes sign and that we have a tangent line. We can also find relative max or relative mins by finding out where the first derivative just changes sign. Notice first derivative is positive and then negative, or negative and then positive. Or if the first derivative is 0 and the second derivative is less than 0, we must have a relative max. And if the first derivative is 0 and the second derivative is positive at a single value, we must have a relative min. We can say a lot about a function just by knowing its derivatives and where they're positive, negative, and 0. In fact, we can say so much about a function because of its derivatives that with them, and using the techniques we already know, we can pretty much sketch a really good depiction of the graph. There's just general steps. So the first thing you always do is you have to find the domain of the function, and if possible, find out if the graph is symmetric or not with respect to the x-axis, y-axis, or the origin. Of course, if it's a function, y in terms of x, you can't have symmetry with respect to the x-axis. The second step is we're going to have to find our derivatives in order to use them, so you find your first and second derivative. In the third step, you then find any critical points, if any, and identify the function's behavior at each one. If it's a critical point, it might be nice to know if it's a relative max, relative min, or just a nothing. On the fourth step, we find out where the function's increasing or decreasing. We can do 3 and 4 by doing the line all at once. In the fifth step, we find our points of inflection, if they occur, and determine the concavity of the curve. We can do all that again by doing a line, but looking at the second derivative. In step 6, we identified the end behaviors That means as x increases or decreases with a bound. Those are your horizontal asymptotes, if any. And we also find all vertical asymptotes if they occur. Finally, you then find any key points where anything is changing, such as intercepts or any of the points we found from steps 2, 3, 4, 5, and so on, and just put it all together to sketch the graph. Let's use those steps to find a sketch of the graph of this function, encapsulating all the important behaviors of that function. So to do that, the very first thing we need to do is we need to find out what's the domain. Now here our domain, just by looking at our function, the domain would be all reals x except x equals 0, because I can evaluate this for everything but 0. The next step is to find our derivatives, which I've already done. Now I need to find where the function is increasing or decreasing, concave up or concave down, in order to find my relative extrema and my points of inflection. All that can be done by following the steps I've done before. I need to know where the first derivative is 0 and where it doesn't exist in the domain of the function. I need to know where the second derivative is 0 and where it doesn't exist in the domain of the function. So let's just do that. Let's find where this derivative is 0, and I'll solve for x. Well, the only way this could be 0 is if x is 2 or negative 2. I'll leave the algebra to you. Also, the second derivative does not exist only where the x here, this x squared, is 0. But that means x would be 0, but that's not the domain, so we ignore it. I also need to know where does the second derivative, where is that equal to 0? But the only way this fraction could be 0 is if the numerator is 0 for some choice of x, and that can't be 0. So I ignore that one. And then I also find where does the second derivative, where does it not exist? Again, in the domain of the function, because if it's not the domain, we already know it doesn't exist. Well, the only way this fraction would not exist for some choice of x is if the denominator was 0. Well, that would then mean x is 0, but that's not the domain. So we get a whole lot of nothing. Next, I'll make a little line. This line will then represent the domain of the function. So I'll put an open circle at 0 because 0 is not the domain. But I'll put a filled in circle at 2, and I'll put a filled in circle at negative 2. Now before, when I do this, I put a first derivative above the line and a second derivative below. Well, let's go ahead and do that all at once. I've put all the numbers that I got from these two steps on the same line. So this still breaks the interval into the domain of the function into subintervals where these functions can't change sign. So then for every subinterval, take a number and this time plug it into both derivatives and just put the correct sign. So if x is more than 2, like a billion, this would then be very close to 0. So the first derivative would then be positive in this interval. If you then take 1, the first derivative would then be negative. If you try negative 1, the first derivative would be negative. And if you try, say, like negative 3, the first derivative would be positive. For the second derivative, just try the same numbers. You'll find that the second derivative is positive in these intervals and negative in those. That then tells me where the function will be increasing or decreasing, concave up or concave down, or where I have my relative extrema. And in fact, do you see how the first derivative changes sign at 2? That means then 2 will be an important point for us. So let's find it. When x is 2, the function is 8 over 4. That would then be also 2. So we have the point 2 comma 2 is an important point for my graph. Also, if you look at negative 2, notice how the first derivative changes sign and we have continuity. So that means by the first derivative test, if you plug in negative 2, you get 2. That point would also be, negative 2. That point would also be a relative extrema. In this case, it would be a relative max because the function is increasing and decreasing afterwards. 0, at 0, the second derivative changes sign, but there's a hole there. that means that the function is not continuous there. If it's not continuous, of course there's no tangent line. So we'll just ignore that. That's a nothing. You don't get a point of inflection there at all. So we get these 2 points. You should also find any x-intercept or y-intercepts. Looking at this particular function, if you try saying this equal to 0, it's impossible. So there are no x-intercepts. And if you evaluate this at 0, that's also impossible. So there's no y-intercepts. That means this graph, whatever it is, never crosses either x or y axis. So let's just graph kind of what we have so far. Now I know that the only thing that's really important is at 2, 2. So I'll go 1, 2, 1, 2. There's a filled in point right here. There's a filled in point right here. And then you have negative 2 and negative 2. There's a filled in point right there. Okay, but we also know that at this point the derivative is 0, and at this point the derivative is 0. So I must have a horizontal tangent line there. Small little horizontal tangent line. Small little horizontal tangent line. I also know that at 0 that the function is discontinuous. Well, I have to also check my end behaviors. So if you take the limit of this function as x approaches 0 from the right, notice that the numerator is 4 and the denominator is 0. Since I'm coming from the right, that means the function is unbounded. And in fact, if x is bigger than 0, the numerator and the denominator are both positive. So I would get infinity. If you take the limit of this function as x approaches 0 from the left, for the same reasons, you'll actually get negative infinity. So at x equals 0, we have a vertical asymptote. So remember, I must go in this direction on this side and that direction on this side. Next, you might wonder, is there a horizontal asymptote? Well, but if you take the limit of this expression, if x gets large, that limit is infinite. So there is no horizontal asymptote for this rational function. But as an extra little neat thing, notice though that you can rewrite that function using long division and write it as 1/2 times x, and then you would have 2 over x. Now that means then if x becomes large, this portion goes away and the function becomes more like this straight line. So this graph has a slant asymptote. It does not approach a horizontal line. It approaches the line whose slope is 1/2. And here is that line. And I can actually say a little bit more, because if x is bigger than 0, this is bigger than 0, so then this function is above the line. But if x is negative, then this is negative, and the function would then be below the line. So I know then that the graph probably never crosses this line either, and it's above it sometimes and below in others. So let's graph the function with what I know. From negative infinity to negative 2, the function is increasing and concave down, so the graph must look kind of like that. From negative infinity to negative 2, therefore the graph is increasing and concave down. So I must have this slant asymptote. The graph must get close to it and always below it. And I must have a horizontal tangent line. So then the graph must look kind of like that. From negative 2 to 0, the function is decreasing and concave down. So now the graph looks like this. Just remember, I have still a horizontal tangent line at this point and I have a vertical asymptote here. So the graph must look kind of like that. From 0 to 2, the function is decreasing and concave up. So it looks kind of like this. And you can kind of see the vertical asymptote kind of is implied. Although these two pieces could be connected, I suppose. But at this point, we have a horizontal tangent line. So the graph must be decreasing and curve in. So it looks kind of like that. And then from 2 to infinity, the function's increasing and concave up. So then it must look like this. Just remember, though, I have to have this horizontal, this slant asymptote. So the graph is going up, certainly, but it looks like it's going towards that line. That is about what the graph looks like. Let's do the same thing all over again, but with this function. I'd like to know what would be an adequate sketch of this function's graph. So the very first thing we need to do is that we need to go and find the function's domain. Now I think it's fairly obvious that if you look at this particular function, that as long as this is defined, the overall function is defined, and that 2 over x is defined as long as the x is not 0. So the domain would be all real x except where x is 0. Next, I need to know where the function is increasing or decreasing, concave up or concave down. To do those things, I need to find where these derivatives are 0 or where they just don't exist. So let's go ahead and find out when is the first derivative. When would that be 0? Well, the only way this fraction can be 0 is if the numerator is 0. But the numerator is 2 times an exponential. That is never 0. So we can skip that step. I also need to know when does the derivative, when will it not exist? Well, the only way this fraction would not exist for some choice of x is if either this denominator is 0, so x is 0, or the denominator of this fraction is 0, which means x squared is 0. Either way, x would be 0. But we ignore that because it's not in the domain, so we get nothing new from there. Then I need to know for what x is the second derivative of 0. So looking at this fraction, the only way this fraction could be 0 is if the numerator is 0, which means that either e to the 2x is 0, which is not possible because exponentials cannot be 0, or the x plus 1 is 0, which means x is negative 1. That is a place where we could possibly change concavity. Also, just by looking at it, the second derivative would not exist if either of these two fractions denominators is 0, which is where x is 0, but that doesn't count. It's not in the domain. Good. So now I know where this function would then be, where the derivative is 0, or where the second derivative is 0, or where either does not exist. So if you draw a line, I'll put an open circle at 0 to remind myself that there is no function value there, so I don't have continuity there. But I'll also put in over here negative 1. That breaks the domain of the function into 3 intervals. I'll put the first derivative above the line, I'll put the second derivative below the line, and for every subinterval I will pick a number and evaluate the corresponding derivative and put a sign on the right side of the line. For the first derivative, this is always positive, this is always positive, this is always positive, this is always negative. The first derivative is actually always negative. Now some people might say that means that it's always decreasing. That would not be true because the function does not exist at 0. So it decreases from negative infinity to 0, union 0 to infinity, and you can't include 0 because the function is not continuous there. But if you look at the second derivative, again, notice that this is always positive for any choice of x. This is positive for any choice of x. This is positive for any choice of x. And this is positive if x is more than negative 1, and it's negative if x is less than negative 1. So then the second derivative is negative in this interval and positive in these other 2. All right. That would then create a sign line for our first and second derivative. If you just look at it, you can see that at this x value, there's a point on the graph because I filled it in, and the second derivative changes sign. That means we must have a point of inflection. So we have at least one important point. That would then be where x is negative 1. So if you plug negative 1 into the function, you would get e to the negative 2. This is the location of a point of inflection for our graph. Now I also have to check the end behavior. So let's look at various limits. Look at the limit of this function as x were to increase without bound. Or in fact, if it does either increasing or decreasing. So I'll put plus or minus. In either case, this expression in the limit as x goes to positive or negative infinity, that will go to 0, which means that by continuity, e to that will go to 1. So this function does have a horizontal asymptote to both sides, both as x is increasing or decreasing without a bound. But if you take the limit, let's check the other cases, let's check the limit of the function as x approaches 0 from the right. Well, that would then mean that if x approaches 0, this is going to 0. So this goes to 0, 2 over 0. And since this is a positive number always, this would then always be positive. And we know that limit then will be unbounded. This goes to infinity. And e to the infinity would be also infinity. So then going to the right, as x approaches 0 from the right, we have a vertical asymptote. The function is unbounded again. It's increasing without bound as you get close to 0 from the right. But, interestingly, if x approaches 0 from the left of the function, small change this time, that would then mean that x is approaching 0. This will then be 2 over 0. This will then be unbounded. It goes to positive or negative infinity. But since x goes to negative infinity, approaches 0 from the left, that means this is, of course, negative. So the division is negative. This is therefore going to negative infinity. But if e is being raised to a power where the power goes to negative infinity, that limit is 1. Interesting. It's 1. That means then that, oh no, what I'm saying, it's not 1. It's 0. It's 0. Because if you look at the graph of e to the x, as x were to decrease without bound, that function goes to 0. Okay, there we go. So that means that the function actually goes to a point as you come from the left. So there is a vertical asymptote, but it's unbounded only one side. We pretty much have enough now to graph the function, but I'm going to plot this particular graph for at least one more x value. If you plug in when x is 1, you'll get e squared. So notice that the function is always above the x-axis because e to anything is positive. Now for scale, when x is 1, I have to get to e squared, and that's like 8 or 9. So you have 1 and then 2, then 3, then 4, then 5, and so on. There's obviously a lot of scale up there. If you let x approach infinity or negative infinity, we approach these horizontal asymptotes. I have a vertical asymptote, but only to one side. That's to the one side. And as x approaches 0 from the left, we approach that point. So we also have the point where x is negative 1. I'll put that right here. I'll put right here. Negative 1. We get to the point of negative 1 comma e to the negative 2. That's really close to 0. So I'll have to kind of just squish it in there. And then when x is 1, I get way up here. I'm way up there. So I'm going to have to change the scale, or else I'll never be able to draw this thing. So I'll have to erase this one little bit I have right here. No way. And remember that the graph is going up there and comes down. So it should be way up here somewhere. That should be a point way up there. Okay, so if I were to graph it, if I look between negative infinity and negative 1, the function is decreasing and always concave down. So the graph looks like that. And that seems reasonable because of the asymptote to one side. So it looks kind of like that, going down in the point. So let's look at the interval from negative 1 to 0. On that interval, the function is decreasing and concave up. So the curve looks kind of like this. So if I were to guess, I bet the graph looks sort of like that going into the point. Over here, the function is decreasing and concave up, so it looks like this. But remember, there's that vertical asymptote. So I bet the curve looks kind of like this. It's coming down probably pretty fast, and then goes in like this. And it goes up this way towards this vertical asymptote, which I just can't draw because of scale. That's it. That's probably what the graph looks like, something like that. And that gives you the basic gist on how to go about using derivatives to find whether a graph is concave up or concave down, to find your points of inflection, and also to give a fairly accurate sketch of the curve. We'll do more examples in class.